Thank you very much. So today I'm going to talk to you from 10 meters from where the press conference that you have looked at is. But of course, I will not show you any new image of a black hole. I will show you something different today. So the talk I'm giving today is based, of course, on work that I've been doing with many collaborators. I list here in particular the ODYSSEUS core team, Greg Hertz, Katrina Espaillat, Nuria Calvet, Kevin Franz, and Will Fisher. But there are also many other people involved in the projects that I will present today, and I want to acknowledge their work. So to give you a little bit of context, I just want to talk briefly about the scientific question we are trying to address in the last years in our field. So when we look at young stars, when they form, they are surrounded by a dusty disk, dusty and gaseous disk, that actually accretes material on the central star. This process gives rise to many observables, for example, the presence of a strong UV continuum on the star and strong emission lines, and re-radiates material that can be radiation that we can then observe. At the same time, there are winds coming from this system, and it's important to have a complete understanding of this process, in particular, if one wants to understand how the protoplanetary disks themselves evolve with time. This is particularly relevant if we want to understand how planets form in these disks. So it's important to study the mechanisms that drive the evolution of disks. And in order to understand this, we must know how the mass accretion rate on the central star and the properties of winds. And how this has been done in the past depends quite a lot on the community you refer to. So in particular, in the American community, people have been using a lot the Hubble Space Telescope and the UV capability of this telescope to study the UV excess due to accretion to the central star and model this with very physical models of shocks onto the central star. And at the same time, they studied the very the absorption, the emission lines present and emitted from hot gas in the UV that can trace the winds arising from the inner part of the disk. In other cases, people, like including myself and other colleagues, mainly here in Europe, have used ground-based spectra, usually mid and high resolution spectra, for example, from the VLTX shooter instrument, to measure the broadband spectra of these young stars and measure the mass accretion rate with simpler models, for example, slab model to reproduce the accretion of the central star. And at the same time, people have been using mainly ground-based spectra to study at very high resolution the emission lines from winds that trace, what are the properties of the winds in the inner part of the disk. These methods are usually similar, they overlap, but they are usually different in the physics behind, and they never been really compared with each other. And this is something that is changing in our field. And this is all started with a decision of the director of the Hubble Space Telescope that a couple of years ago decided that they wanted to invest about 500 orbits of HST time to study stars in the UV. They decided to focus half of the time on massive stars, and I will not mention that anymore, and the rest of the time on young stars, so young, low mass stars. As soon as this news was out, it was clear that it would have been public data, which is key for this talk. We decided as a community to start to put together all the knowledge we have and to start to coordinate in the way we want to best use this data. So we contributed to the selection of the targets at the very beginning, and then we decided to put together a proposal to get funding through the HST to fund work of postdocs and PhD students, and to start a broad collaboration where everyone should be involved and should be able to collaborate on getting the best out of the data. So this team called ODYSSEUS is something that is a place that now has hundreds of collaborators worldwide And this is really where we coordinate the efforts on the data, as I will show later. At the same time, we obtain data, we obtain time on the Very Large Telescope, the one you see in my background, to actually carry out a large program on the same target of the Hubble Space Telescope and simultaneous in time. And what I really insisted on is that I wanted to use the same strategy as the Hubble observations. In particular, I wanted that the data are public as soon as they're taken. And this was something that I wanted to do because I wanted this data to be a service for the community, to be available to everyone, so that what we get out of the data is the best science possible. And I want to note that many other people are working with the same attitude. So many other people are getting photometry from small or larger telescopes. People are getting high resolution spectroscopy from small telescopes worldwide. And we are coordinating with TESS, and we are really starting to exchange information among us. So briefly on the program, for now, we'll have, for once, we'll have a complete view of spectra of young stars from the near ultraviolet to the end of the to the near infrared, with almost contemporaneous observations that are always public as soon as they're taken. So everybody can access this and can do everything that we have always been doing for years in the different fields in the different countries. And this is for us a game changer, because we are covering with these observations the whole evolution of protoplanetary disks, different stellar masses. And so we are trying to approach our scientific questions with a totally different view. I wanted to spend two minutes saying how do we share the data among ourselves. So the data taken from HST are usually quickly processed in the team and shared on a Slack channel that we have. On the same Slack channel, we have ancillary data, for example, photometry from ground-based telescopes from TESS that is shared to everyone. Everyone in the team can use it. And on Slack, we also started to coordinate observations. So let's say that the Very Large Telescope was unavailable for a short time during the COVID. Then other people jumped in to take spectra at the same time. The idea then was to share all the data, the Hubble data, on Zenodo, but soon after, the HST on their own organized the reduction of the data, and they are putting them the fully reduced data on a dedicated website. On the ISO side, on the Very Large Telescope side, we're using a very similar strategy. So we have a Teams channel, Microsoft Teams channel, where we put not only the final reduced spectra, but also the intermediate steps in the reduction and the scripts that we're using for flux calibrating the spectra and to combine the different exposures between the spectra. We are also exchanging information on how to remove the tellurics and so on these channels. We also upload there for the team the fully reduced spectra, so flux calibrated, telluric corrected, and so on. And these are available to the whole team. After we collect enough data, we are uploading them on Zenodo so that they are quickly available to the whole community. And we are then planning to put them with the way that Magda described before on the phase 3 archives to be available to the whole community. And this, I want to say that this is something that, in my opinion, is helping us to move from what I described at the beginning of the talk of different communities doing things at their own way to a very different way of doing science in our field. Indeed, we are sharing among the ODYSSEUS team the list of projects that one could carry out with the data. And we are assigning, a lead, a contact, highlighting if this is a project related to a PhD thesis or a young postdoc, also to help young researchers to get the possibility to work on the data and on the specific topic they would like to work on. And one of the interesting results for me of this exercise is that there are more ideas than we thought at the beginning. There are more things you can do on the data than we thought at the beginning. And especially in this case where we have a lot of data, this is really interesting. And the other nice aspect is that people are starting to combine their methods and their analysis. So on the left hand here, you see an image from a paper I published where you see the combination of the VLT extruded spectra and the HST spectra, where in the HST we cover the UV part, and we're trying to test the models that we have been using, even in that regime that it's not covered from the ground. And on the right-hand side, you see a paper that we published earlier this year, where the opposite is done. So starting from the models that very well fit the UV, they're trying to check whether they can fit even the infrared part of the spectra. And this is something that they can obtain simultaneously only thanks to the simultaneous observations with the very large telescopes. So to conclude, I want to say that, in my opinion, making public surveys, making the data public, is really a key to enlarge and encourage collaborations. And that, in my opinion, it would be nice that the telescopes, that the big observatories really encourage even more these public efforts as a service for the community. Thank you very much.
Thank you very much, Carlo, for that nice talk and overview on how you work together. Let's see in the Slack channel if there are questions for you. I don't see anything yet. I do have a question myself. So this is clearly a collaboration with like many wavelengths and everything combined. What do you think in this collaboration made it such a big success, and was it easy to get everyone together and get started on this? Because it's not an easy task, I guess.
No, I mean, this is a very very deep question in a certain way. So I think what helped a lot is that we were already starting to collaborate among some of us, and we started to, and a few key persons in the different communities actually proactively contacted their own communities. So and we were like at least 4 or 5 from different communities, and this helped a lot. And the other thing, I think in this specific case, is the big effort comes from the Hubble Space Telescope. I mean, they put a lot of time, they invested a lot of time, so much that they changed the momentum. In a certain way, it became clear to everyone that there would have been enough data for everybody. And this, I think, is key. It's like they put in so much time, 500 orbits of HST, that's a lot. This is where we will work on in the next years, clearly.
Thank you. Very clear answer. Okay, I don't see any more questions. Oh wait, now I see one. Mohammed Aklaghi asking, thank you, Carlo. Did you consider putting the data in CDS? It allows interoperability, for example, finding nearby objects by RADAC in other datasets.
Yeah, so that's a very nice. So thank you for this question. No, I actually did not yet consider that. I think that also in the view of this conference, it's interesting for us to understand also better what is also an easy way to share the data. And an advantage I've seen in Zenodo personally is how quickly you can get the fully reduced data available to everyone, so that you can upload things in very simple formats with very little additional information that is anyway sufficient probably for experts to have a first analysis of the data. I will then proceed with the phase 3, because as Magda, with the phase 3 ZISO for the VLT data, because as Magda said, this is something that for large programs we are asked to do. CDS is something that I can consider, and I will definitely, I mean, if they want to get in touch with me, I'd be happy to discuss this possibility.
Okay, thank you. Just checking. I think that's it for now
Yeah.
for questions. If more questions appear, keep
I will be
checking
on
the
Slack
Slack
or
channel.
write me.
Perfect. Thank you.